Okay, so for question 2, normal heptane is dehydrocyclized to toluene and hydrogen in a continuous vapor phase reaction as so. So pure heptane at 400 degrees Celsius is fed to the reactor. The reactor operates isothermally at 400 degrees Celsius and the reaction goes to completion. So the data is given here that the average heat capacity of N-heptane between 25 degrees Celsius and 400 degrees Celsius is 0.2427 kilojoules per mole per degree Celsius. So A, taking a basis of 1 mole of heptane feed, draw and label a flowchart. B, taking elemental species C and H2 at 25 degrees Celsius as references, prepare and fill in an inlet and outlet enthalpy table. C, calculate the required heat transfer to or from the reactor, state which it is in kilojoule. What is the heat of heptane dehydrocyclization reaction at 400 degrees Celsius and 1 atm? So this is a very simple diagram. Basically, you have an inlet feed and an outlet. So inlet contains heptane, and your outlet contains toluene and hydrogen, N2 and 3. Okay, we will name this as N1. So this is your reaction. Okay. So we take elemental species at 25 degrees as references and prepare and fill an inlet-outlet enthalpy table as so. So we assume that the reaction proceeds at stoichiometric reaction and steady state, and we take the basis of 1 mole of heptane. Now this is an open system operating at steady state, so our energy balance will be simplified into delta H is equals to Q. We will use the heat of formation method since all the components are involved in the reaction. Okay, you have this, all of them are involved in the reaction. So again, your heat of formation formula. So we will use table B.1 for the value of the heat of formation of each species here, which is the 3 species, heptane, toluene, and hydrogen. So we start off with heptane, we call it H1. So the heat of formation of heptane in table B.1 is negative 187.8 kilojoule per mole. And we were given that the average heat capacity of N-heptane between 25 and 400 degrees Celsius is this value. Okay, so we do not have to calculate the A, B, and C in. It has been calculated. So we calculate them from 400 to 25 degrees Celsius. So we get negative 96.79 kilojoules per mole. So for H2, which is your toluene, so the heat of formation of toluene is 50 kilojoules per mole, and we integrate its latent heat from 400 degrees Celsius to 25 degrees Celsius. Okay, again from the table obtain the A, B, C, and D values and substitute the temperature that we integrate from in. And that leaves us with 110.17 kilojoules per mole. Okay, so for H2, the hydrogen. So in this case, hydrogen is involved in the reaction. However, from table B.1, the heat of formation of H2 hydrogen is 0. Therefore, we have 0 here, and this we only have to calculate for the latent heat from 400 to 25 degrees Celsius. Okay, substitute your A, B, C, and D for H2, and we get 10.89 kilojoules per mole. So we fill in H1, 2, and 3 back into the inlet outlet enthalpy table. Okay, simple. Now C, calculate the required heat transfer to or from the reactor in kilojoules. So Q is equal to delta H, and that we have this equation. Outlet minus the inlet. So N, the outlet Ni is toluene and hydrogen. Okay, let's check the equation again. Okay, toluene and hydrogen, so we have 4 hydrogen here. Hydrogen, toluene, minus the inlet, which is 1 mole, multiplied by its H enthalpy, specific enthalpy, I'm sorry. And that leaves us with 250.52 kilojoules. Okay. D. What is the heat of heptane dehydrocyclization reaction at 400 degrees Celsius at 1 atm? So in this case, since there is no inlet in this system, the heat reaction when 1 mole of heptane reacts is equal to the change in enthalpy as we found in part C, which is about 250 kilojoules per mole.